All right, kiddos, here we go with projectile motion. So here's an example of projectile motion. Throwing the football, go long. I got this. These terms are here just so you know what you should be learning and have words to discuss. Basically, a projectile is anything that's in the air that has only one force acting on it, and that is gravity. I'll write that down. That's a good one. Okay. Object in motion, only gravity acts upon it. So, the somewhat counterintuitive thing, I think, for students is that here you are, you throw a football, and the football's in the air. There's our football. There's nothing pushing it forward, right? As soon as you let go of the ball, it's simply the ball's momentum that is carrying it in the forward direction. Gravity acts downward on it, so there is a force acting on it, and that is gravity. But everywhere along its path, there's only one force acting on it, and that is gravity. And the force with which gravity acts upon it is the same. We call that the ball's weight. So there is an acceleration, and the acceleration is negative 9.8 meters per second squared. So the ball leaves your hand with some vertical velocity that is decrease and decrease and decrease and decrease and decreased, and then we get a negative vertical velocity that increases and increases and increases, and this horizontal velocity remains constant. That's weird, but that's the truth. So we can say horizontal velocity is constant, and we'll get to that. So when we talk about horizontal and vertical component of velocity, you'll see in the example something that's thrown at an angle like this. We can use our SOHCAHTOA skills, and don't pretend that you don't have those. We can use our SOHCAHTOA skills to figure out, well, it's just a right triangle. How fast is it going horizontally to the side, and how fast is it going vertically? So we would call that horizontal velocity and that vertical component of some velocity at some angle. Just you wait. Okay, so the main concept involved in projectile motion is, here we have an example. So I am holding a bullet, and I'm also holding a gun, and the gun has a bullet inside it. And what's going to happen is the gun is going to go bang, and the bullet is going to go like that. Now the reality is this is not drawn to scale, okay? But the bullet is actually going to trace the path of a parabola, right? And so that's somewhat parabolic. But the bullet is going to hit the ground. Actually, this is definitely not drawn to scale. So the bullet's going to take this parabolic path and hit the ground. Obviously, the gun fires the bullet very quickly, so it has a very large horizontal component of velocity. But the reality is that the fact that the bullet is moving to the side does not affect the fact that it is falling. So the bullet that I'm holding in my hand is going to fall, and the bullet that comes out of the gun is going to fall as well. And this bullet and this bullet are actually going to hit the ground at the same time. And frequently students are like, I don't believe you. You think of the gun as something that just makes this go infinitely far or whatever. It is moving to the side, so this would be, several hundred meters or something, depending on what type of gun it is. But the fact that something is moving to the side, so I'll say this in words. Horizontal motion and vertical motion can basically be treated independently. So we'll see some videos, we'll do a lab, it'll start making some more sense. Let's talk about some examples here. let's talk about some examples. Okay, yeah, I put it down here. Sorry about that. Okay, so on the second page, we have two situations. So one, we're going to do a lab just like this. We have a ball rolling horizontally off the table, and the question gives us some information, the mass of the ball, its horizontal speed, and the height of the table, and it asks where does it land, and when does it land. So by where does it land, we're talking about that distance, or I'll write it as displacement. And when does it land, we're talking about t. So t equals what if, right here, the instant the ball leaves the table, we're calling that t equals 0 seconds. Okay, we can solve that. And more complicatedly, we have a situation where we have a marshmallow launcher. This is a pretty fun lab, especially if you can catch them in your mouth. So the marshmallows launch with a speed of 8 meters per second at some angle, 50 degrees. That means with respect to horizontal. So like that, 30 degrees, so this is 30 degrees with respect to the horizontal. It's less common to hear with respect to vertical. So we want to know how high does it go, meaning that height. How long is it in the air, meaning time when it lands back on the ground, and how far does it go, meaning this horizontal distance. Okay, solutions look like this. Oh wait. So first example. So I would be reading and I would be drawing this. 500-gram tennis ball. I knew that was extraneous information, so I didn't write it. But the 500 grams is mass. It doesn't matter. 500-gram tennis ball with a speed of 2 meters per second. So a horizontal velocity, and I would write in 2 meters per second. All right. Falls off a 1 meter tall table, and so I have listed the height, and I've shown it in my diagram as 1 meter. All right, and I know that has some vertical velocity eventually once it starts speeding up downward. So see how I've broken this given information into horizontal and vertical. So when we're talking about horizontal motion, the horizontal velocity is 2 meters per second. The acceleration is nothing, all right? The horizontal motion is unaffected by the vertical motion. The reality is that we will experience, the ball will experience some air resistance, but it's negligible, and we assume it's 0. All right, we basically don't do any calculations involving air resistance. It's very complicated. So horizontal velocity stays the same, acceleration is 0. We want to know how far it goes. So x equals question mark. The initial horizontal position we're saying is 0, so this would be a horizontal position of 0, and this would be our horizontal position of x. And okay, so that's our information. In terms of the vertical, so as it leaves the table, it's moving to the side. So its vertical velocity is 0 initially. This is a v naught, a v sub 0. That's whited out right there. Oh, okay, whatever. So that shouldn't be there. All right, so notice the difference between horizontal velocity is 2, but it's not moving up and down. Initial vertical velocity 0. Acceleration negative 9.8 meters per second squared. We assume, and it's a pretty good assumption, we are on Earth, all right? Unless it's stated otherwise, this is an assumption. This is something that's not stated in the question, but it is implied. And it's falling off the table, so the initial position is a height of 1, and the final position, it lands on the ground, is 0. So I kind of set this up before even thinking about the fact that it was moving to the side. So the fact that the ball is moving to the side does not affect the vertical motion. This would be the same as if you were standing there and dropped the ball. It's going to drop at the same time, or land at the same time. So based on this, we want to know time, all right? When does it land? So we want to know time right here, t equals question mark. And so based on that, I chose this equation, which is kind of our formula of the month, in order to solve for t. So position 0 on the ground, initial position 1, vertical velocity times time 0, and 1/2 acceleration t squared. And so we get 0.4518 seconds. I put a bunch of decimal places because I knew I'd be using this later. So this, when we're asking when does it land, we could say 0.45 seconds, and I think we actually only have one significant figure, so technically we would have to call it that. And how far does it go? So notice how we used information that we got from the vertical motion, the time, to figure out how far it actually goes. So we know it's moving to the side with this speed, 2 meters per second. We know it's in the air for 0.4518 seconds. And so notice how I can use the simple equation. This is just distance equals rate times time that you've been using since 5th grade or whatever. Because for horizontal motion, the acceleration is 0. This equation is basically just this equation with that term equals 0. So we have initial horizontal position is 0, velocity in the horizontal direction is 2, and the time in the air is 0.4518 seconds, and multiplying 1 sig fig gives us 0.9 meters. This would be the answer to where does it land? And to be specific, we could say something like, where does it land? 0.9 meters from base of table. Okay, I'm worried that I'm going to exceed my 15-minute limit, so we're going to have a part B to do the marshmallow question. I know, you can't wait.